What's up, chemistry class? Leilani and Yuliellis. I got my glasses on today, so I'm feeling extra smart, alright? So I hope you watched the last video answering the questions from last week, and I hope that all made sense. And if it didn't, write me an email and tell me, and I'll try to make another video to make it make more sense. Okay, so this week we're talking about how atoms differ. It's the next lesson EduSystem. I'm going to assign it, so you'll go on EduSystem. It should pop up that I assigned it, and you go through that whole PowerPoint, and then watch this video too, and then at the end you'll do the questions. So most of this should be review, I hope, and yeah, but if it's not, I think there's going to be some new parts, and there's going to be some math, so don't freak out, take some deep breaths, it's going to be okay, okay? I wish we had class, but here we are online. All right, hopefully your guys' week's going good, and you don't feel too stressed. Okay, so we left off last week, right? We knew that the nucleus had protons and neutrons, and the electrons were moving around, right? So now there is this guy came along, Henry Moseley, and Moseley figured out that each atom has a unique number of protons in the nucleus, a unique charge in the nucleus, which you guys know. So please, I hope you have a periodic table. If you don't, like Google one. You need to look at the periodic table for this stuff now, because it'll help you identify the trends that are happening and what is going on, okay? So here you go. Here's hydrogen. I don't know if I'm too far away. You can see that. But either way, you can look it up. Okay, so hydrogen, the name hydrogen, right? I'm just showing you an example. The atomic number is the whole number, like the 1. It doesn't have any decimals, it's the whole number. That's how many protons and electrons each atom has, okay? So hydrogen has 1 proton, 1 electron. The chemical symbol is an H, and the average atomic mass, we'll talk about that in a sec, 1.008. That's an average of the different isotopes. Don't worry, I'll explain the isotope in a sec. But what you need to know for now, right, is Moseley was this big knowing that each atom has a different number of protons. So like helium has 2, lithium has 3, beryllium has 4, and you can keep going through the periodic table and you can see how many protons each element has, okay? So, the atomic number equals the number of protons, which equals the number of electrons. And that's the whole number on the periodic table for each element, okay? So, what is an isotope? Here we go. Okay, so isotopes are atoms with the same number of protons, but different numbers of neutrons, okay? So what that means is, as far as identifying what element it is, that's protons, okay? Protons and electrons. But there can be different numbers of neutrons. And the different numbers of neutrons doesn't change what the atom is, it just changes the weight, okay? And that's called an isotope. So isotopes are different, they have different numbers of protons, different numbers of neutrons, same numbers of protons. That's very important, okay? So the different numbers of neutrons doesn't change the chemical behavior. What changes the chemical behavior is the different numbers of electrons, okay? Not neutrons. So isotopes all behave the same, okay? So, for example, you have potassium. Look at potassium. It's a K. I don't know who decided that, but its chemical symbol is a K. Okay, it has 19 protons and 19 electrons, all right? But there's 3 different isotopes of it, okay? You have one has 20 neutrons, one has 21 neutrons, one has 22 neutrons, okay? So if you look at, on your periodic table, you look at the atomic mass, which is this number, remember? The decimal. If you look at the decimal number, right, you'll see that it is a decimal. It's an average of those 3, the 3 different numbers of neutrons. The atomic mass is the average of that. We'll talk about how they calculate that. But what that means is, on the periodic table, whenever you find potassium, you'll find it, and it'll have all 3 different isotopes. It'll have different percentages of each isotope, okay? That could be confusing. I'll talk about it again in a sec, okay? But here's how it works. Isotopes with more neutrons have a greater mass, but they behave the same chemical behavior. So they're still potassium, they just are heavier, okay? Chemical behavior is defined by how many electrons. So electrons are what? changes the behavior of the atom, not neutrons. So even though potassium with 22 neutrons weighs more than potassium with 20 neutrons, they both behave the same. Chemically, they both behave the same. Okay? That could be confusing. I keep pushing my glasses up. I've been having allergies, so I'm using my glasses today. So they're kind of reflective, so hopefully it's not weird on the video. But the important thing, isotopes have different numbers of neutrons, but they have the same chemical behavior. They just weigh more, okay? So, we're going to come over here, and I'm going to try to explain this. Is there any questions so far? I guess, did I miss anything? I think, hopefully that's pretty straightforward. Just isotopes, different number of neutrons, same number of protons and electrons, same chemical behavior, they're just heavier. Okay. Alright, here we go. So we have the mass number. What is the mass number? It is the atomic number, right, which is the whole number, plus the number of neutrons, okay? So, for example, we use isotope notation, which means, for example, copper. Copper is Cu, okay? Copper. We'll find it on your periodic table. Okay, you found it? Copper. So let's say there's a couple different versions. One has 34 neutrons, right? So here, if you add 29, which is how many protons it has, plus 34, you get 63. So it's copper 63. We call it copper 63. Or another version has 36 neutrons. Oops. Has 36 neutrons, and you add 29 plus 36 gives you 65. And that is the atomic mass number, okay, for that. Isotope notation. 65, we call it copper 65 is the name, all right? So in nature, most elements are a mixture of isotopes, okay? We'll come back to potassium. This is potassium in a banana. If you eat a banana, bananas have potassium. They're good. Potassium's good for you, okay? 93.26% of the isotopes that are in the potassium you eat in a banana have 20 neutrons, okay? 93.26% have 20 neutrons. 6.73% have 22 neutrons, okay? 6.73% have 22 neutrons, and then only 0.01% have 21 neutrons, okay? But, like, no matter how much of the banana you eat, that is the percentage of isotopes that you were eating, okay? So what that means is the atomic, so we'll talk about, I'm going to calculate this in a sec. The atomic mass of the potassium is 93% with the 20 neutrons, 6.73% with 22 neutrons, 0.01% with 21 neutrons. And so you calculate that, and that is how you get the atomic mass number that is on the periodic table. It's an average of all the different isotopes together. So when you find potassium, you'll find different percentages of each isotope. Okay? Hopefully that made sense. So that's important. It's a mix. Everything's a mix. So, like I said, we talked about isotope notation. So you can practice. There's sample practice problems in EduSystem if you want to do some, if you're still confused, because it walks you through a couple of them, which is what I'll do right here. So let's say you have neon, right? Neon's atomic number is 10. Its mass number is 22. They give you that, okay? So you would say, how many neutrons does neon have? Well, 22 minus 10 equals 12. You take the number of the total number, the mass number, and you subtract the protons. That gives you 12 neutrons, okay? And you call it neon 22 because that's the mass number. So you write it like this. 22, neon 10. Neon 22 is the name, okay? We call it neon 22. So let's talk about atomic mass units. So this is kind of confusing. So basically, the way that the units that are used in the periodic table are atomic mass units, okay? And it's an atomic mass unit, we call them AMUs, or you can just call them units sometimes. 1/12 the mass of a carbon-12 atom. So that means the isotope of carbon-12, 1/12 of that is 1 AMU. Now they picked carbon-12 because carbon's abundant in life, and it's confusing to explain, but that is what they picked as a reference for the atomic mass unit, okay? And it's important to know that one proton is almost the same weight as one atomic mass unit. You can look on any system. It's like 1.008 AMUs is one, atomic mass units is one proton. I think 1.008, okay? But it's not exactly the same. It's not 1.000 forever. It's 1.008. So they're not exactly the same. So while one AMU is very close to the mass of a proton, it's slightly different, okay? So if we want to calculate atomic mass so that you have different isotopes, and you're like, well, how much what's the atomic mass and what element is this? So here's what you do. Pull up. Hopefully you have a calculator. Here's my calculator. Aha. Okay. Here, this is the example from EduSystem. Oh, sorry about that reflection. There's no shades in here. I don't know. But okay. So the way it works, you have this we don't know what isotope this is. It's isotope 6, and this is isotope 7. And they give us the mass, the atomic mass units, okay? 6.015, 7.016, and the percent abundance, 7.69%, 92.41%, okay? So we have two isotopes. This one, the isotope 6, is only 7.69% abundant, and isotope 7 is 92.41% abundant. So as far as abundance goes, it's a lot more abundant, isotope 7. So what you do, the mass contribution from isotope 6, you take mass times percent abundance, okay? Let's do it. You take the mass, so you go 6.015 times 0.0769, right? Because 7.69% is 0.0769. And you get marker's not working. 0.4, come on, marker. 0.424625. Hopefully you guys got that. Okay, 0.4625. And you do the same with number 7. So you go 7.016 times 0.9241, 6.4834. Okay? Now you add those two together. Plus, summa. Okay? And what do you get? 6.94. Is that right? Yes. Good work. Go team. 6.94. 6.941. Okay? I guess you got 6.946. But you get a number close, okay? AMU, atomic mass units. Okay, and what is the closest on your periodic table? What element has the closest number to that? The 6.41. It's lithium. Lithium. Which is Li. Okay? So you calculated that. Your closest number you found was 6.41 atomic mass units. That's how much lithium weighs. So your mysterious X is actually lithium. Okay? So you calculated that. So you have to add the two up after. You calculate it with each percentage, you add them up, you get the total atomic mass units, and then you see how much they weigh. Okay? And you can tell, I put this other example over here with fluorine. You can tell fluorine has an atomic mass, atomic mass units are 18.998. So you can tell the most common isotope is fluorine 19. And you can sometimes tell that, you can't always, but it's a cool little trick. You can read about it in the EduSystem too. Okay? So you can look at it and see that it's close to 19. You're like, well, the most common isotope must be fluorine 19. Okay? So now you know how to calculate. You can watch it again if you need to. Now I want you to do questions 20 to 24 in the review for the lesson, how atoms differ. And I'll send you in an EduSystem. All right. See you guys next week. Let me know if you have any questions. God bless you.